Hello, this is Andrew Gabor, CTO and President of BrightSpot Automation. I'm going to talk today about photoluminescence imaging for perovskite solar cells and solar panels. I'd like to also thank the Department of Energy for their R&D support. So BrightSpot Automation's business model is to sell photoluminescence and electroluminescence testing equipment for solar cells and solar panels. We sell testing equipment for the entire PV value chain, from research to product development to manufacturing to deployment. We're based in Boulder, Colorado. We've been around for over 13 years and have over 250 customers worldwide. Our current growth markets are in space solar and perovskite solar cells and solar panels, and that's what I'm going to be talking about today. We're a leader in this area with 13 industrial customers and 7 academic customers. Manufacturers and researchers for perovskites have many challenges. Some of those relate to electrical defects, such as shunts that you can see in this image here, either along the scribe lines or between scribe lines in the active area. There's material quality variations, manufacturing drift and variations, and then there's reliability issues as a function of different types of stresses. And most of these problems you can't see by eye, and that's why we're selling these non-contact metrology tools to see these defects. First, a little background on PL, or photoluminescence. The principle is that we use LEDs to shine on the solar cell or solar panel with energy that's higher than the band gap of the semiconductor, so it creates electron hole pairs. When these electron hole pairs recombine, they give off light, and we can detect the pattern with a camera over the solar cell or solar panel, and the non-uniformities or variations in intensity in the image tell us about the problems. Now, since photoluminescence is a non-contact characterization method, we can actually apply it prior to the point where you could inject current to perform the more common electroluminescence imaging. So prior to the deposition of a metal electrode, we can still perform the photoluminescence on the partially processed solar cells. Even after we have metallized the sample, you still may want to do PL, either because it's faster or easier, or you get some complementary information to that provided by electroluminescence testing. Our tools can be used for any type of orientation of the solar panel. Here we show our cell spot tool that's on the left is oriented in a sunny side up orientation, and on the right is to the side orientation. You can test samples as large as 36 centimeters in size, but if you have larger panels, then our plus spot tool can be used. This particular model can test panels up to 120 centimeters in size, and this model has been installed at a manufacturer both after the perovskite deposition step and after the electron transport layer step. It has excellent uniformity of LED intensity and is very stable intensity both during a test and from test to test due to feedback control. We can customize this tool for any desired size. Right now we're building our largest tool yet, able to test a full-size utility scale panel. This will go to a customer wanting to test first solar cadmium telluride panels or standard silicon utility size panels prior to installation in the field. Here is a PL image of a cadmium telluride panel, or a portion of a cadmium telluride panel with a 120 centimeter tool. You can see a variety of shunt defects, spatial non-uniformities, and a crack in the front glass that has disturbed the circuit. In this image of a copper indium gallium diselenide panel that has undergone partial shade induced damage. You see many very hard shunts in the solar panel. And this is another close-up view of a cadmium telluride panel that's undergone partial shade induced damage, where we have trained our Impel AI automated defect detection and grading software on these two different types of shunts, those that touch the P4 scribe line or those that are elsewhere within the panel. For those folks who are interested in monitoring the variation in band gap from panel to panel or even within a panel, we can do this by using a filter wheel in front of the camera. And we can install, for example, 3 different filter stacks within that wheel, one to look at the left side of the spectral emission, one for the center, and one for the right. And then we can do some simple math to look at that drift. For example, a simple ratio of one intensity to another. For those folks looking at tandem solar cells, we can look at both the top and bottom junction in both electroluminescence and photoluminescence mode. For electroluminescence mode, we simply will take one image with a filter stack corresponding to the emission spectrum of the top junction and then shift to the filter wheel position for a different stack that corresponds to the emission of the bottom junction. Photoluminescence is a bit different. There we will excite the top junction using short wavelength light, such as a blue LED light, and similarly use the correct filter wheel location. And then for the bottom junction, we will use near infrared light that will pass through that top junction and then be absorbed in the bottom junction, and use the different filter wheel position for that. Our Impel software works on the concept of recipes, where a recipe contains any parameter that is involved in the system. So, for example, your power supply settings, such as current and voltage, camera settings, such as gain and exposure time, the filter wheel position, any post-processing you want to do. All those are saved in a recipe, and you can recall recipes for different applications. We also have this concept of multi-step imaging, where with one trigger of the system, we can take a whole series of images. In this example that I show here, we are taking first an electroluminescence image of the top junction, then a photoluminescence image of the top junction, then an electroluminescence image of the second junction, PL of the second junction. Then we apply a stress, in this case, voltage bias. It could be forward or reverse bias. And then we image again. If you get a system with a DC power supply to do electroluminescence imaging, you then for free can do dark IV scanning. And what we can also do, some added functionality within our software, is allow the user to shift that curve downward into the 4th quadrant, and then we can do curve fitting and extract some figures of merit of that curve, such as efficiency and fill factor. With the photoluminescence light sources and the addition of electronic load, we can get light IV scanning capability. This is monochromatic light IV though, so it's not an accurate spectrum to the sun, but it is quite repeatable and of value. And our software can auto-collect scans over a wide range of intensities, and we can also compare those scans to 2 other curves. One, the pseudo-IV or SUNS VOC curve, is absent any series resistance effects. And then another curve, the implied IV curve, is extracted from the photoluminescence images we collect at each irradiance level. And this type of curve eliminates any additional contact effects. We can also plot a figure of merit plot called the optical ideality factor from those series of PL images collected at different intensities. Again, this is all non-contact imaging. And there's 3 other figure of merit plots we can do in non-contact mode. These are implied figure of merits for open circuit voltage, fill factor, and conversion efficiency, doing some additional mathematical analysis. If you have that electronic load, we can take images in quadrant 4 of the IV curve, biased PL images. If we take 2 images near the maximum power point, we can then also plot figure of merit plots for J0, the series resistance, and the conversion efficiency. So our tools come factory ready. In terms of automation, we have a variety of different data transfer communication approaches, different ways of integrating that software and exporting the data, different ways of securing such that no cloud connection is required, so it can be very secure. Even the training and inference of the AI model can all be done locally on site. In terms of equipment control, we can control a variety of systems such as the probing station that you see here. So if you have any questions, please contact us at the email address shown here or leave a comment in the comment section. Thank you.